everyone, I am Pragya Srivastava. I am here to record a lecture on control system AKGEC 602. Previously in my lecture we have studied unit 5 and we were studying frequency domain analysis. We were studying this analysis for open loop transfer functions when the variation of parameter was with respect to frequency. So in my present lecture we are studying the introduction to polar plot, and then we are going to study the assessment of stability and how we can calculate gain margin, phase margin from the plot, and then we will comment on stability, and then we will see few numerical problems. In this we have introduction to polar plot. To sketch the frequency response means to plot the variations in magnitude and phase with respect to frequency. What happens to the magnitude and what happens to the phase when the variations are with respect to input frequency? The two plots constitutes of frequency response and are called gain plot and magnitude plot, and we have the magnitude plot is also called the phase plot. We have also studied in polar plot the magnitude plot is dg omega hg omega, and it is plotted against the phase angle of dg omega hg omega for various values of omega. We have also studied which is the magnitude, it is the phase. The polar plot is the locus of tips of the phasor of various magnitudes plotted in the corresponding phase angles for different values of the frequencies from 0 to infinite. We will be studying that how we can study more on polar plot. Let's say these are the different values at omega equals to 0. We have seen that omega equals to 0. The magnitude is this and the phase angle is this much. So we have located this point. So we can see that this is the axis, this one is the imaginary axis, and this one is the real axis. So we have to fix a point by allocating or by assigning a magnitude and a phase to that value. Let's say I call about 2 at an angle of 90 degrees. So if it is 1, this will be 2. 2 at 90 degree. So 2 at 90 degree means this is 0 degree and this is 90 degree. So 2 at 90 degree will be nothing but this point. So let's say this is 5 at an angle of 45 degrees. So I have plotted P0. Similarly, for omega equals to 1, I will be having some magnitude and some phase. So magnitude is P1 and phase is phi1. At omega equals to some other value, magnitude is P2 and phase is phi2. At another value of omega, the magnitude is P infinite and the phase is here phi infinite. So this is how we can conclude this. Now, moving ahead, consider a system with open loop transfer function as GSHS equals to 10 by S, and we have to obtain its polar plot replacing by S as j omega. Now, we are writing it as 10 by j omega. We are also writing it as 10 plus 0j and here 0 plus j omega. We can see here the imaginary part is 0 and here the real part is 0. Now, the magnitude of course is 10 by omega. So, magnitude is 10 by omega. So, for different values of omega, we have magnitude. So, when omega equals to 0, magnitude is infinite. When omega equals to 10, the magnitude is 1. When omega equals to 100, the magnitude is 0.1 and so on. Now, concluding the angular information. Angle is phi tan inverse. For the numerator, we have imaginary by real. So, 0 by 10. For denominator, we have tan inverse imaginary by real omega by 0. So, it is 0 and 90 degree, and then we have minus 90 degree. So, for all the values we have the phasor at minus 90 degree. So, the polar plot would start, we will start and terminate at phi equals to 90 degree. So, we start with omega equals to 0. For omega equals to 0, we have infinite as magnitude. So, this is the starting point. For omega equals to 10, we have magnitude as 1. For omega equals to 100, we have magnitude as 0.1. And then for omega equals to infinite, we have magnitude as 0. So this polar plot can be drawn like this. This is the polar plot. This is the required polar plot. Now, introduction to polar plot, we have to consider type 0 system where open loop transfer function is given by GSHS is equals to 1 upon 1 plus TS, where T is constant here. And we have to obtain the polar plot. Now similarly, we have to split it into real and imaginary. So this is 1 plus 0 j omega, 1 plus j omega t. Now the magnitude, when the magnitude is concerned, it is 1 upon root over 1 square plus j omega square. Now phase angle is, from the numerator side we have tan inverse imaginary by real 0 by 1, tan inverse imaginary by real omega t by 1. So this will give me 0 degrees and this will give me a variable which is minus tan inverse omega by t. So for different values, now I am ready to make a table. So again I'll have different values of omega. For different values of omega, I'll have different values of magnitude from here, and then for different values of omega, I'll have different values of angle. Now using this, I am ready to make a polar plot. So this is the required table. For 0, it is 1 and 0 degrees. For omega equals to 1 by t, it is 1 by root 2 and 45 minus 45. And similarly, we can plot it. Now, for 0, magnitude is 1, phase is 0 degrees. So magnitude is 1, phase is 0 degree. For 1 by t, 1 by root 2 minus 45. So minus 45 is this one. So 1 by root 2 is this one. So this is the next point. For another frequency, 1 by root over 101 and angle is this. For omega equals to infinite, we are nearing 0 and minus 90 degrees. So we are entering 0 and minus 90 degrees. So this is the required polar plot here. The corresponding polar plot is shown in the figure. So this is how we can understand the concept of polar plot. Now we have to see the assessment of stability. The stability information of the system can be obtained by merely looking at a point at the polar plot. So if the polar plot gets closer to minus 1 plus j0 point, the relative stability reduces and the system tends toward instability. Now let us consider a characteristic equation 1 plus GSHS equal to 0. We can rewrite it as GSHS equals to minus 1. So minus 1, here we can see that when we are studying for any stable system, we are taking and equating the transfer function to 0. Now we are equating the open loop transfer function to minus 1. So my point of concern should shift to minus 1 j0. So let's talk about a point where minus 1 comma j0 is studied. Now minus 1 comma j0 is here, minus 1 comma j0 is here, and minus 1 comma j0 is here. As the polar plot gets closer to this point, the relative stability reduces. So here we can see that these are the two poles, and for the corresponding two poles, the plot is like this. The plot is like this. Here we can see the plot is like this. Again, for if the poles have shifted here, the plot becomes like this. Now we can see if any other, there is a slight change, the plot will come to minus 1 comma j0, and sometimes it can overlap. So from here to here, the system is losing the tendency to become stable. So it is moving towards instability. Assessment of stability. This given figure shows the polar plot of GSHS equals to 1 upon S into 1 plus T1S into 1 plus T2S. It crosses the negative real axis at omega equals to omega 2. So negative, so it is the positive real axis and here is the negative real axis. So we can see that where is the polar plot? Here, from here we can see the polar plot. Let's see the polar plot. I'm drawing the polar plot like this. This one is the polar plot. So polar plot is crossing the negative real axis at omega equals to omega 2. Now, here this distance is called A. This is the intercept A. Now, one more thing we have to do. We have to draw a unit circle. Unit circle means a circle which have the magnitude as 0. So, let me draw. This is the unit circle. So, here also we are drawing a unit circle. So, this is the unit circle. Now, let the unit circle center at origin pass through -1, j0, intersect the polar plot at frequency omega equals to omega 1. Now, this is another new frequency where the unit circle intersects omega equals to, where the unit circle intersects the polar plot. Now, we have two frequencies here. One is omega equals to omega 2, where the polar plot intersects the negative real axis, and omega equals to omega 1, where the polar plots intersects the unit circle. Now, let the phasor omega GJW1, GJ omega 1 make an angle of phi with the negative real axis and measured positively in counterclockwise direction. The relative stability can be measured in terms of intercept A and phi and angle 5. These concepts are used to define gain margin and phase margin as practical measure of relative stability. Now, we can see that moving ahead on this, we will see the point at which this omega is crossing, this polar plot is crossing the negative real axis will be taken as a frequency at which, if we take the reciprocal of that magnitude, gives me the gain margin. And similarly, from here at this frequency, if I calculate the phase, if I calculate the phasor, and that phasor will give me the phase margin. So, from here we can see how to calculate gain margin. In figure, we see omega equals to omega 2. We are clear with this point. The phase angle is 180 degree and the magnitude is A. If the gain of the system is increased by a factor of 1 by A, then magnitude of GJ omega H omega becomes 1 into A into 1 by A, that is equal to 1. So, therefore, gain margin may be defined as the reciprocal of magnitude at the frequency at which the phase angle becomes -180. Now, we can see the phase at which the phase angle is -180 is called a phase crossover frequency. So, from here we can see that the gain margin will be equal to 1 by A. 1 by A means the reciprocal, and here A will be nothing but gain at omega equals to omega 2. So, what we have to see? We have to trace this frequency. At this frequency, we have to calculate the magnitude and we have to take the reciprocal of that magnitude to get the gain margin. Now, so in this case, the gain margin will be -20 log A. Now, comes the phase margin. Phase margin will come from this frequency omega equals to omega 1. At omega equals to omega 1, we will calculate the phase. So, for this value of phase, we will put this formula, and from here we can get the phase margin. Therefore, phase margin is defined as the amount of additional phase lag at gain crossover frequency required to bring the system at the verge of instability. So, in addition, phase lag will be equal to phi is introduced in the gain crossover frequency, and the phase angle will become -180 while the magnitude remains unity. So, this is the concept of gain margin and phase margin from the polar plot. Now, from here we can comment on stability. The stability of a control system based on relative relation between gain margin and phase margin is listed below. If the gain margin GM is greater than 1 and phase margin is positive, the system is stable. We have studied this in previous lecture as well. If the gain margin is equal to the phase margin, it is called marginally stable system. And if the gain margin is less than 1 and the phase margin is negative, we call the control system to be unstable. So this is about the comments using which we can comment on the stability of the system. So using this we can comment and we can predict the stability of a system using polar plot. Thank you.